video. Okay, there was a question about some of the Alex problems where you have to know when something's liquid or solid or gas on the elemental side of things. And so if you'll look at this periodic table that you get in class or in the test, it's kind of subtle, but right here you see mercury, it's italics. It's in italics. And so is bromine. Bromine is in italics. Okay, so those are the only two elements that are liquid. Down here at the bottom, there's a little key that says elements in italics are liquid. So bromine and mercury, elemental forms, would be liquid. The elements that are bold-faced are gases. So you go up here, the bold-faced ones. So helium, nitrogen, oxygen, fluorine, all of the bold ones are gases at STP, standard temperature and pressure. So that's the basis for the enthalpy of formation, and we'll talk about that today. It's forming any compound from its elements in their standard states at 1 atmosphere and actually it's room temperature, 298 Kelvin. Then that would be the enthalpy of formation. We're going to talk about that today. But here it is on the periodic table, and then all the other ones are solids. So like palladium, it's not bold, it's not italics, and so you could know the palladium solid would be 0 enthalpy of formation. So that's how that's going to go. I'm not sure what the Alex periodic table looks like. We can pull it up, but this is the one you get on the test. So that information's on there. Okay, let me just swap that back over. Turn this off. Okay, we're set. Okay, so I guess instead of doing Alex reports, I did like a little bit of the exam grade. So a few A's got knocked down to B's with this one, but I'm okay with that. I think you still have a chance of getting back to the A range. Hammer it hard. I'm not going to move the cutoffs. Like someone's right at an 89 or something like that, and they're like, man, give me that 1 point. Give me, maybe at the end of the semester. If I'm looking at that and I'm sort of saying, there's a group here of folks that have performed really well, and then there's a group here and there's a kind of a gap. Then I would say this 89 person is performing with the 90s, 91s, and 92s, and the 87 person or 86, if there's a bigger gap, is performing with the Bs. And so I would make the cutoff 88, right? Because that's where the groups kind of naturally break. And so that's how I do the curves at the end. I kind of look for natural breaks. Same for the BC cutoff or the CD cutoff or whatever. The CD cutoff, that's a more important cutoff, obviously, because if you're going to continue on in science, you need a C or greater in this course. You're going to go on to 1412. And so I look at that one, I really scrutinize it, and I want to make sure that you're engaged, you're coming to class, you're doing the work. And so, so attendance in that case really plays a role. If someone is just sporadically attending, they're at that DC cutoff, it was like, hey, you got to care enough to come to class, right? So that's where here's lots of absences. So these are the absences, the little red marks. So good job being here. Folks that aren't here, get another little red mark. Okay, so those absences correlate to performance. And so this is the absences along the x-axis. I realize you can't see the numbers, but there's like a 99% correlation, 94, 96, 97% correlation in performance on Alex and on the exams with attendance. And that's surprising because honestly, coming to class, I do like show you how to do some of the Alex problems, but Alex is really on you, on your time. So I would not expect class attendance to lecture to really correlate with Alex as strongly as it does. But I think, correlation is not causation. We typically think of correlations as causes, but they're not. So I think that the organized lifestyle that gets you here at 9 in the morning is also the organized lifestyle that schedules time for Alex. And the disorganized lifestyle that doesn't lead you to getting here at 9 in the morning is also the disorganized lifestyle that doesn't schedule time for Alex. So I think they're both correlated to the decisions you make on a daily basis. And so let's jump into today's material. We're going to be talking about thermochemistry. And that's what I was joking about with the meme. We've got molar mass, and we've got molarity and percent composition and titration and all of that stoichiometry stuff. And then we're just adding one more thing, thermochemistry, which can be used in a stoichiometric manner to learn how much energy we get out of equations. So this is a really exciting part of the course for me because I'm a physical chemist, and this is physical chemistry. So physical chemistry is learning about how chemistry connects to the physical world. And energy is one of the best ways that chemistry connects to the physical world. It's how we run our automobiles. It's how we air condition our buildings. It's all of those things. It's the thermo part of chemistry. So that's what we're talking about today. So this is enthalpy. That's a funny word, a new word for you. Enthalpy, that just means heat. So enthalpy of reaction, that's just the heat of reaction. And we can just take the products and their enthalpies and subtract the reactants and their enthalpies, and we get that difference, and that's the enthalpy of reaction. Now we need, let's see, think of altitude. In my mind, I think of energy as a landscape. Just like you look out in a valley and you see the hills and you see the valleys and so on. And you know that, water and pine cones and things roll downhill. Okay. Well, nature does the same thing energetically. Okay. So energy wants to go downhill. So thermodynamics wants to go downhill. So if your reactants are up here in terms of energy and your products are down here, it's going to release heat. It's going to roll downhill and release heat. Okay. But we need a reference point. What is our reference point for altitude? Do you know? Sea level. Yeah. So sea level is our reference point for altitude. So in energy, we need a reference point, right? So I want to be able to put everything in a table. Like I could list a list of altitudes only because I have everything relative to sea level. If I didn't have a reference point, then it would be real hard to make a table. So one of the most useful things is a table, right? Because then you could take differences. Before we can get a table, we need to figure out what our reference point is going to be. And so we're going to form our compounds from their elements. So our elements are the reference point. So in sea level for altitude, our elements are our reference point. That's our sea level. So we're going to say that it costs 0 energy to form the elements, because that's what nature gives us. So if nature gives us these elements, we're going to start there, and then we go uphill or downhill from the elements. And so this is an enthalpy of formation reaction right here for water. See, we're making water out of hydrogen and oxygen. So hydrogen gas, that's an element nature gives us. Oxygen gas, also an element. And we balance that equation. We form 2 moles of water. And this is the amount of heat that's given off. That is an enormous amount of heat for puny little 36 grams of water. You give off, 483 kilojoules. That's pretty good. If it does that, if you were able to get that done in a second, a joule per second is a watt. And so if you could make 36 grams of water in a second, okay, then it's giving off 483,000 watts. Think of your generators. You go to Home Depot or to Harbor Freight and you buy a generator, a big old box generator is like, 2,000 watts. So 2 kilojoules per second. So it's an enormous amount of energy given off. In fact, that's what the space shuttle used to get into orbit, was mostly the hydrogen-oxygen reaction. It had some solid rocket boosters, but 75% of the thrust came from this reaction, hydrogen and oxygen making water. If we were to reverse that reaction, then it would be uphill. So you can think of this minus sign as downhill. The hydrogen and oxygen were here. It formed water. It went downhill. So it released that heat when it formed water. Water was more stable. We could push it uphill. If we had water and we wanted to go back to the elements, we got to decompose that water. We got to break it apart, make the hydrogen, makes the oxygen. We're going uphill. So you see that plus sign is showing that that's endothermic. And so we have these terms, endo and exothermic. So this negative sign indicates exothermic. And this plus sign is endo. And this is just a screenshot of the textbook. This just helps. Okay. So exothermic releases heat. The heat is exiting. That's the way I remember it. Endothermic is going inside the reaction. Okay, and so this is that reaction of water. We got hydrogen and oxygen in a balloon. Stick it with a hot stick. Boom, blows up. And this energy level diagram is a really important concept in science. We could draw the two different states of our energies with these lines. So this is the state here. And in fact, we can go ahead and put a line right here and call that 0. That's the elements in their standard states. So that is 0. And now we know this one is minus 486 or something. What was the number? Do you have it?
483.6.
Okay, 483.6. So that's the energy of that state. Okay. And so it's downhill. So when it drops downhill, it's exothermic. It gives off energy. It's a negative number. Okay. Okay, so let's get into Alex. If we reverse the reaction or double it or cut it in half, this is we do that to the enthalpy number. So here's a reaction that Alex gives us. This says use this information to complete the table below. So look at this reaction. We've got water plus oxygen making hydrogen peroxide. And what do you say about this plus sign? Endothermic, right? So this is going uphill from water and oxygen uphill to hydrogen peroxide. And so then what have we done here? Notice hydrogen peroxide is now on the left, so it's a reactant. The coefficients are the same, so all we have to do is just change the sign. We reverse the reaction, we change the sign. Yeah. So water and oxygen went uphill to hydrogen peroxide. If we reverse the reaction, it's downhill. And so it's a negative. Okay, uphill's positive, downhill's negative. What about this next one? Okay, it's written the same way. Water and oxygen are on the left. This time we're only forming 1 mole of hydrogen peroxide. We've obviously divided everything by 2. And so that's all we have to do for this one is we just have to divide that 196 by 2. Because if you divide the whole reaction by 2, you can also divide the enthalpy by 2. So this is how much material you have. And so if you could think about, going downhill, uphill you had, 2 moles of water and 1 mole of oxygen, and you went down and formed 2 moles. Actually, we're going uphill. 2 moles. We tore apart 2 moles of water and a mole of oxygen and formed 2 moles of hydrogen peroxide, and it was uphill, 196. If we cut all our material in half, we're only going to get half the energy, or have to put in half the energy, right? So this enthalpy is what we call an extensive property. Okay, if you double the mass, you're going to double the enthalpy. Cut the mass in half, you're going to cut the enthalpy in half. It makes sense. I mean, if you're cooking your stove, right, you double the amount of gas, you're going to double the amount of heat that you get out. Oh, you would do the math and then type in the number. Yeah. And so this is 98. Okay. So that's half the number of moles, and so you cut it in half. Okay. And then this last one, you have to kind of figure out what went on. We've flipped it, so now it's going to be a minus sign. And then when we go from 2 to 6, what have we done? Multiplied by 3. So we flip the sign and triple it, and then that's what we end up with. So the minus sign is because we reverse the reaction. And so it's 3 times the moles, and it's reversed. So the minus sign is because it's reversed, and then the 3 is for the 3 times the moles. So those will be pretty easy on Alex. You just got to inspect what you're given, see what they did to it. Okay. Questions? Okay. All right. Okay, so now we're calculating the heat of reaction. We're giving us this enthalpy of this reaction, and then we can look at this. This is testing if you understand the vocabulary words endo and exothermic. So we're looking at the minus 55.3. So which one do you click? Exothermic, yeah. So I got the little star there, and then suppose 33.5 grams of nitric oxide or nitrogen dioxide react. Will heat be released? And so this question, this part of the question is just seeing if you understand what exo and endo mean. So it's exothermic. So you're like, yeah, heat will be released. That's what exothermic means, that heat is released. Okay. And then if you said heat will be released or absorbed in the second part of the equation, calculate how much. And so here's the stoichiometry part. So we know that we've got 33.5 grams of NO2. So we're going to want to switch over to moles. Okay. And then everything in this reaction is equal. So this is 55.3 kilojoules equals 2 moles of NO2, and that's also equal to 1 mole of N2O4. So you can write out those conversion factors and use them in problems. Now, one thing I would like to point out is that whenever we say released or absorbed, those words can take the place of the plus or minus sign. So let's pay careful attention to this problem. First step is super easy. This is what you've been doing this whole time, is to calculate the molar mass. So 46 grams per mole for NO2. Okay. And then look what I've done here. I put a positive 55.3 kilojoules, but I put a little subscript that says released, because it's asking how much heat was released. The word released means it's negative, okay? And so it's 55.3 kilojoules released per 2 moles of NO2. Don't forget that 2. So you look at the reaction, whatever the reaction has, if it's a 5, if it's a 1/2, whatever, you put that in the problem, okay, as your conversion factor. And that will keep you from being off by a factor of 2. But this is why that value that you enter into Alex is positive 20.1, because it's just saying how many joules were released. That word released means the negative piece. Does that confuse anybody? Okay. Okay, so we could probably do more on this other stoichiometry, but again, it's just the only trick here is this step right here with the 2. Okay, so you got to go from the equation, whatever the number is for the joules, pairs up with whatever the coefficient is too. So it's 2 moles NO2. All right. Now let's talk about Hess's law. This kind of ties in. Remember when we did the balancing redox reactions, where we had the 2 half reactions, and then we added them together, kind of like a mathematical equation. You know, if I had 3A on the left and 3A on the right, I could subtract them from both sides and they would go away. That's the principle of this Hess's law. I can write reactions forwards and backwards, and I can change the sign on delta H, and I can add them together, and I can make new reactions. So I can take the formation reactions, an element formed from its a compound formed from its elements, and I can write these forwards and backwards, and I can take compound 1 and 2 and react them to make compound 3 using Hess's law. So let's look at this. So here's an example problem from your textbook. The enthalpy of reaction for the combustion of carbon to CO2 is here, minus 393 kilojoules per mole of carbon, and the enthalpy of combustion of carbon monoxide to carbon dioxide is minus 283. Use this data to calculate the enthalpy of combustion from carbon to carbon monoxide. So we want to go from carbon here. We want to go from here to carbon monoxide. But yet they're both reactants. But all I need to know is that I've got to have carbon in one reaction, and I have to have carbon monoxide in the other reaction, and I can flip one, and I can make this one a product. Okay, so what I'm going to do is I'm going to leave the first one. Let's see. Yeah, so first one, I'm gonna flip this second reaction so that carbon monoxide is a product. You see, it's right here. And so whenever I flip that reaction to make it backwards, I flip the sign on the enthalpy. And then I'm going to add that to the first reaction. Carbon solid is already a reactant. Okay. And then I'm going to add these together. Okay, so when I add these together, I've got a half a mole of oxygen on this side. So I'm going to cancel out 1/2 of these, and I'm going to make this 1/2, right? And I've got a CO2 on the left, and I've got a CO2 on the right. And so when I add these down, this is my net reaction. Is everybody okay with that? I have 1 oxygen on the left, a 1/2 of oxygen on the right, so I can cancel a 1/2 from both sides, and I end up with just a 1/2 on the left. Carbon solid comes down, no change there. The CO2s cancel. There's the same on both sides, so they can cancel. And then now I add the enthalpies. Okay. So I have 283 minus 393. So that's using Hess's law. You see, if we have a table of reactions and their enthalpies, then we can use those tables and we can reverse this reaction, multiply that one by 2, cancel the things that are the same on both sides, and then we can do the same thing to our enthalpies, change the sign, divide by 2, whatever we need to do, and then add them together, and we'll get a new reaction. We'll get a new enthalpy of reaction. So that's how we use Hess's law to come up with new reactions. Once we build a big enough table, then we can do all kinds of chemistry. In fact, we can put this in a computer software and it'll do it for us, and they have software that'll do that. So let's now apply this to one of the Alex problems. So using Hess's law to calculate the net reaction enthalpy. So the lead acid storage battery is the oldest rechargeable battery in existence. Can you believe we've been using them since 1859? That's crazy. Okay. Still 150 years later. Okay, there's 2 reactions that take place. In one step, sulfuric acid decomposes to form sulfur trioxide and water. In another step, lead and lead-4 oxide and sulfur trioxide form lead sulfate. So calculate the net change. So let's analyze now what Alex is asking us to do. Calculate the net change in enthalpy for the formation of 1 mole of lead sulfate. So that's important. So this is the formation of. So this is going to be the arrow, right? We're going to form 1 mole of lead sulfate. From. That tells you we're talking about reactants now. From lead, solid, okay? From lead-4 oxide, okay, here. And from sulfuric acid. So these have to be on the reactant side. So the reason I'm paying so much attention to that is I've got a table up here, and it's showing that, I don't have to flip them, but if I did have to flip them, then I would have to move them around so that sulfuric acid would be on the reactant side and so on. So our reactants look like they're fine, except for this one. This is forming 2 moles of lead sulfate, and we only want to form 1 mole of lead sulfate. So I'm going to have to take this one, and I'm going to have to divide it by 2. But otherwise, they're written in the correct order. Okay. So we'll keep that one as is because H2SO4 is a reactant. And we're going to cut this one in half to make only 1 mole of the lead sulfate. So here's the problem. So here's our first reaction, and here's our second one, everything cut in half. So we have a 1/2 mole of lead, 1/2 mole of lead oxide. We still have this SO3, and then we're making 1 mole of lead sulfate, and we've taken the enthalpy of reaction and we've divided it by 2. And then we can look at this reaction and we can say, yeah, that this sulfur trioxide is going to cancel. So add everything together, and this is our reaction. We have 113 minus 775 over 2 is negative 275 kilojoules. Type that in, you got it. Yes? Say that again? because the problem specifically said we want to form 1 mole here of lead sulfate. Okay, and so if we look at this reaction, we see this reaction is to form 2 moles of lead sulfate. So if we run that reaction and as it's written, it forms 2 moles of lead sulfate and we get 770 kilojoules, but we only want to form 1, so it's going to be half the amount of energy that comes out of it. So again, it's directly proportional to how much material you're making or breaking is the energy that you get out of it. So if you double the amount of gas, you're going to get double the heat. So when you turn the temperature up and you want it in the winter time, because we're heading in, you double the amount of heat you want out of your natural gas. You're gonna double the amount of gas you use because you're doubling the amount of heat, and you're also going to double the cost. So this is just Hess's law shown in terms of the energy level diagram. And so you can see that you can go any direction in these reactions. You can go straight from reactants to products, or if you don't have this reaction, like let's say you look in the table for this reaction. So the products are methane and oxygen, and I'm sorry, the reactants are methane and oxygen, the products are CO2 and water, and you're looking for that combustion enthalpy, and you look in the table and you don't find it. Okay, but you're like, well, phooey, what else do I have in there? Well, I've got a reaction from methane to carbon monoxide and water and oxygen, and I've got a reaction from carbon monoxide to CO2 and water. You could use those 2 reactions to get your answer. Okay, so if you go this way, step 1 and step 2, and add those together, you'll get the energy that you want. So now that we've set up the elements as our sea level in terms of energy, we can make tables. And so these are the standard enthalpy of formation tables. There's a bunch of them in the notes. There's one on Alex as well. The one on Alex is really long. Okay. And you've got, you can pretty much make any element in here, any compound in that table relative to its elements, you can now put the amount of energy it takes to form that substance. Now there's a few in here that are positive. What does that tell you in terms of like acetylene? Acetylene has a positive enthalpy of formation. It's what? It's endothermic to make it, yeah. But what are we making it from? For these enthalpy of formations, what are we starting with? Carbon and hydrogen, the elements in their standard states. And nature gives us the elements, right? That's our sea level. We go out and we find hydrogen, we find carbon, and we make acetylene, and it's uphill. So what does it tell you about acetylene? It doesn't even want to exist thermodynamically. It would rather be carbon and hydrogen. So it's a pretty reactive molecule. And so if something's really, really positive in terms of its enthalpy of formation, it's an unstable compound. Not necessarily unstable, but it's unfavorable thermodynamically. It's uphill from the elements. If it just decomposed to its elements, it would give off energy. If you react it with oxygen and it goes below the elements, it really gives off a lot of energy. And that's why we cut steel with oxygen and acetylene, because acetylene is uphill from hydrogen and carbon, and hydrogen and carbon react with oxygen already, so that's exothermic. So this is even more exothermic. So you could react oxygen with carbon and have an exothermic reaction, or you could react oxygen with acetylene and have a really exothermic reaction. So it's a great. In fact, it's so unstable and reactive that we can't just put acetylene in a tank. We have to separate it from other acetylene molecules. So we fill that tank with acetone, with a solvent, and then we pump the acetylene in. So the acetylene tanks in a welding situation have got liquid in them. You hear them sloshing around. That's the stabilizing solvent that we have the acetylene dissolved in. And the acetylene wants to come out of that solvent pretty badly, and it gives a good pressure. So that's that's showing you the amount of energy we get out of acetylene when we react it with itself, or even more so with oxygen. Can you get that door back there? Here's ethylene gas too. It would probably work, but you see acetylene's even better. Okay. Okay. Once we get to ethane, now we're getting into negatives. Okay. So we've reacted enough hydrogen with the carbon. This is interesting too. This says diamond is positive. So diamond is not the elemental form, the most thermodynamically stable form of carbon. Do you know what is? Do you know the different forms of carbon? There's 3 well-known forms of carbon. But diamond is one of them. What's the other? Graphite. Yeah, graphite. And then they discovered another one a few years back, 20 years, 30, probably 30 years ago, the buckyballs, the Buckminster fullerenes, all these magic numbers of carbons making these spherical and tube shapes. That's a third allotrope of carbon that was discovered, and they got the Nobel Prize for it. It was pretty cool. But graphite is the thermodynamically stable one. So diamond is uphill from graphite. Okay, but it's very stable, but it's uphill. So it would release a little bit of energy if it became graphite. So you can maybe get by with giving a graphite ring and say, I got you the most stable form of carbon. Instead of a diamond ring. Don't think that would go. Oh, well. It's worth a try. But if she's a chemistry major, she might appreciate it. Graphite engagement ring. I don't know. Don't try it. It's not as pretty for sure. Okay, so write a standard formation reaction for chromium nitrate. So again, we're forming this compound from its elements. So these ought to be pretty easy. The only thing about these on Alex is it's tedious to do the subscripts and superscripts, but you just hammer your way through it. So what we're doing is we're forming the chromium nitrate solid. Okay, and this is where you probably have to do the solids and liquids and gases. Okay, so you got to get those correct. So it's very simple to start with the chromium because we got chromium solid. So we type in the CRS, okay, and then the nitrogen. So nitrogen comes in pairs, it's N2, and so here we have to do the 3 halves. We can't double everything because we want to form just 1 mole of the chromium nitrate. So that's why we have to keep it 3 halves. Now, how do I know it's 3 halves? Well, look here. I need 3 nitrogens, okay? And they come in pairs. So when whatever this subscript is, I'm dividing by that subscript. So if I take N2 and divide it in half and multiply by 3, I've got 3 atoms of nitrogen. Okay, so I'm taking half of a nitrogen molecule and multiplying that half, which is just 1 atom of nitrogen, times 3. So that's where that just confuses the heck out of some people. Okay, now the oxygen, I've got 3 times 3, so there's 9 oxygens. And so I'm taking an oxygen molecule. I'm only taking half of it, which is 1 atom of oxygen, and I'm multiplying that half by 9 atoms of oxygen. So this gives me 9 atoms of oxygen, 3 atoms of nitrogen, and I've got the chromium, and that makes chromium nitrate. These are gases. Okay. If I had bromine in here, I'd have Br2 liquid. That would be the thing. If I had mercury in here, I would have Hg liquid. So the 2 liquids will get you the mercury and the bromine. The gases, nitrogen, oxygen, fluorine, learn the gases, and everything else is solid.
Mercury HG.
No, I think it's just going to be mercury liquid, Hg. Yeah. Sulfur might catch you. It's S8. I don't know if I don't know if Alex is going to give you sulfur, but if it did, the elemental form of sulfur is S8. And so if I needed 5 atoms of sulfur, I would have to divide by 8 and multiply by 5. So it would be 5/8 of an S8 to get 5 atoms of sulfur. That'd be the hardest one I could come up with if I was writing these. Okay, would give you sulfur. So if this was chromium sulfate, let's just do that. Here we are, okay? Okay, we're going to have to balance these out. This is going to be chromium 3 plus, SO4 2 minus. So it's going to be Cr2, SO4 3. Yeah. So we have 2 Cr solids. And here I have 3 sulfurs. And they come in groups of 8. So I have 3/8 of an S8 solid. Crazy, but that's what it is. Okay, and then oxygen, I have 4 times 3, that's 12 oxygens. So I'll go ahead and do this. So that's oxygen gas. If I did 12 halves, I could simplify that, right? 12 divided by 2 is 6. So I could scratch that out and put a 6 there. Does that make sense? So there we have formed the formation reaction for chromium sulfate. And these guys here have 0 enthalpy of formation. So if we did this reaction and measured the enthalpy of this reaction, these are set to 0. And so it would be the enthalpy of this reaction would be the enthalpy of formation for this substance.
Now, is that the answer we put into Alex, or do we take the 3/8 and just call it 3?
No, you have to do the 3/8. Yeah, so you have to put in a fraction and do a 3/8 S subscript 8 and put the solid. Sounds like it's asking for the solid because it does matter what the elements are. And so here we have the even more enthalpy of formation tables. Let's see if there's anything interesting on this one. Notice some of the most negative ones. Well, first of all, the more atoms you join together, the more negative it is. Okay, and also the oxygens. When you add the oxygen to things, you get really low energy. So oxidation reactions really give off a lot of energy. And then also the more elements you have, like look at sucrose over here. Sucrose, negative 221. Again, you've got a lot of atoms in there. 12 carbons, 22 hydrogens, 11 oxygens. So the bigger the molecule, the more energy is released as you form it from the elements and so on.
So is propane just a lot more stable than acetylene?
Yes. Mm-hmm. So think, we haven't gotten to double and triple bonds yet, but the carbon atoms and how they're bonded together, when you completely saturate, the carbon can bond to 4 things. When you put a different element or elements on all 4 of those spots on carbon, that's the lowest energy. But if you start taking things off and making carbon bond with itself, it's more higher energy. And so acetylene has a triple bond, so it's even above the elements. So let's do some more. Here's enthalpies of reaction to calculate enthalpies of formation to calculate enthalpies of reaction. So here's a combustion reaction. So here's propane burning with oxygen to make CO2 and water. And we could look at those enthalpies of formation. And one way to think about this is our propane is a reactant. And so we're taking it apart. So we're taking the propane apart. So we're taking apart the reactants. We don't have to pay any penalty to take apart the oxygen, really, because it's an element in its standard state. So the enthalpy of formation of oxygen is 0. But we have to take apart the reactants, and so that's where this negative sign comes from. So this is the delta H of formation for propane. By writing this in reverse, we get this negative sign. And then if we look at CO2, we're forming 3 moles of CO2. And so we would take that enthalpy of formation reaction for CO2, and we would multiply that by 3, because we're making 3 moles of that. And we're making 4 moles of water. So we take that formation reaction for water, we multiply by 4. And so then we can cancel terms like the 4 hydrogens cancel, the 3 carbons cancel, the let's see, what else? Anything else cancel? We have 5 oxygens, so no, everything adds up. 5 oxygens, 3 CO2s, 4 waters, and now the enthalpy of reaction is all 3 of these terms added together, see. So this is what's happening when we use those tables to make enthalpy of any kind of reaction we can think of. So if you can find all your parts, all your pieces of your reaction in one of those tables, you can flip them backwards or whatever you need to do, multiply by 5, multiply by 2, add them all together, and you can calculate the enthalpy of any reaction you can think of. It's really great.
And is it that 5.26 is just a number, right? It's not the actual.
Where?
On the side of 5.26, 5.27.
Oh, that's it from the book. I just copied this from the book. So these are the equation numbers in chapter 5. Yes. Yes. Okay. Good. We back up. This one.
Yes. So whenever you have it nitrate,
Yes.
you don't break it down to the reactants. You always break it down into the single element.
Because of this word right here. Standard formation. So when we're talking about a formation reaction, that means from the elements. Yeah. Otherwise, we might just be talking about an enthalpy of reaction. So the formation reaction is a particular type of reaction. We're making it from the elements. Whereas this one, like this is a combustion reaction. So this down here at the bottom, when we finish this, you see it just says enthalpy of reaction. It doesn't have a little F here. The enthalpy of formations, that little F means you get that from the table. So when you see a delta HF, that F is a formation, and that's from the tables. So we can put those table numbers in here. We put the water table number in here, multiply by 4, the CO2 table number here, and multiply by 3, and we take the propane table number here, and we change the sign, because it's a reactant. We got to take it apart, so we pay the penalty for that. And then we sum those together and we get the delta H of reaction. Now, it just so happens this is a combustion reaction, and so this would also be called the delta H of combustion. So we could write that as a different table, and we could have the combustion reactions for all the different fuels. So here's an Alex problem using the same kind of thing. Use the table of formation enthalpies under the Alex data tab to calculate the reaction enthalpy for this reaction under standard conditions. So this is the general equation. We take the coefficients and their enthalpy of formations for the products, so that 2 would be there, and the 4 would be there. We go look up the table values for CO2 and for water, and we add all those together. That's the products. And then we subtract all of the reactants, because we got to take this one apart. So here's that data table. You click on that, you get all of these substances, and you got to scroll down until you find the compound that you're interested in. And I do these in table format. So I start with the products. So I have plus 2 CO2s and plus 4 waters. And so notice how the units cancel out. I got 2 moles of the CO2, and the CO2 table value says it's minus 393.5 kilojoules per mole. And so that per mole cancels with the 2 moles, and I just end up with kilojoules over here. So for this reaction, the end result is just going to be kilojoules. It's not going to have a per mole on the end. Okay, the per moles were canceled in this middle column. The 4 waters is 4 moles of water. This is the data from the table. The green value, okay, came from this table. So that's color matched. Okay, and then the reactants, and notice this minus 2 alcohols and minus 2 oxygens. So minus 2 moles, and this is the alcohol number. So I had to scroll through, find the carbon molecules, and find methanol. That's what this compound is. And found it in here. That green value is from the table. The moles cancel, and it's a minus sign. So minus times a minus gives me a positive value here. And then the oxygen, I went ahead and wrote a row for oxygen, even though you don't need to, because oxygen is an element in its standard state. So its enthalpy of formation is 0. So it doesn't matter how many moles of oxygen I need, I don't have to pay for it. Nature gives me the oxygen. So that's the beauty of it. I don't have to pay for my oxygen. Yes?
Question. So if it's a reactant, the beginning part of the mole is going to be negative?
If it's yes, this right here, that's where the reactant is indicating here, this negative sign. And it's exactly the same as our minus 2x, minus 3x, positive, positive. The reactants have those minus signs in them on the table format and even on the enthalpies of formation. This is where people mess up, though, right here, is they don't cancel that negative. Like if they have a negative enthalpy here, they don't cancel that negative sign with the reactant. They see the negative sign and they're like, oh, yeah, that's a reactant. And they feel like they've already canceled it, but they haven't. So minus 2 times the minus 238 is a positive 477. That's going to cause you to be wildly off in your values if you forget that negative. Okay, but this is the beauty. We don't pay for our oxygen. So that's why there's really no conspiracy with fossil fuels. I mean, there may be some, like 2% conspiracy. The rest of it is just the facts that we don't have to pay for our oxygen. Okay. If you're running a battery, you got to pay for the oxidant and the reductant, the oxidizing agent and the reducing agent. You have to produce both of those. Fossil fuels, we poke a hole in the ground, oil comes out, we burn it. We're only paying for half of that, right? And so we add all those together. This is the enthalpy of combustion for this.
It's any element you'll never have to pay for.
Right. Well, I mean, I say pay for, like pay for an energy penalty. We may still have to, like for mining or something like that. Like copper, nature gives us the copper in its regular form, but we do, quote, have to pay for it to get it away from the ore because it's reacted. So we got to run it uphill till they get to an element, and then it's ready to go. Yeah. Yes.
So oxygen will never have to like truly worry about that calculation. We can just do it if we want to.
Yeah, and I just show this zero just to show that it is by definition zero. Same for carbon solid, graphite, or S8 sulfur solid.
Well, it always work that your ending kilojoules for reactants are positive.
No,
Okay.
like acetylene,
That's
right? So it would be a positive number here, and so it would be negative over there. Yeah. Yes.
What all like elements are like oxygen where we don't have to like worry about it?
I would just put them in there, and then when you look at the table, see up here, this table is really nice because it says aluminum solid 0, right? So if aluminum solid was one of your things, you would have a 0 right here in the green number, and you would know I don't have to worry about that one. I don't have to calculate that row. I can just write 0 kilojoules. Yeah. So all your elements in their standard states. And what do I mean by standard state? State of matter, right? Solid, liquid, gas at room temperature, 1 atmosphere. So my kids, we were hiking through the woods. Funny story. And Grandma found this sandstone, and she picked it up. It looked just like Oklahoma. And she said to my kids, "Hey kids, what state is this?" Okay. And my son said, "Oklahoma." And my daughter said, "Solid." And I said, "You're both right." So anyway, it was a really proud dad moment. She was like, "Solid." So, yeah, I'll go ahead. Go. Yeah.
Are we gonna have to remember the state of matters?
On the obvious ones, I would say. Yeah. Like oxygen, nitrogen, and carbon.
So like common ones?
Yeah, the common ones. Yeah. And just go by Alex and see what you see. Like if there's a weird one like sulfur, beware. Like go back here and look, see if they put S8 on there. I bet they do because that's the accurate one.
I think I remember that.
Yeah. And so like the 5/8 thing or whatever I did, that you may have to do that. Yeah. Yeah.
So, this is kind of like what I wrote down for like notes for the
Sure.
exam. I remembered part of it, like while I was in the exam. Like,
Oh, I didn't look at it.
There's some of them, like the calculate the formulas. Like this one, I was doing okay with it. I was like, okay, I know that the mole is
It wasn't
6.02,
Yeah, like on the other number.
and then times 10 to the 23rd, and then, but like there was one, and I'm like, I know one of the formulas has like times 100, and now I'm remembering it was this one.
Percent composition?
Yeah, I was like,
Uh-huh.
which one is it? Because I was originally like on the exam, I was like, is it that one?
Uh-huh.
And I tried it. I'm like, no, it's not, because I didn't get any of the answers on there.
Okay.
And then, but I did the other formula. I'm like, okay, that's one of the answers
Okay.
on here.
Did you figure it out, you think?
And no, I don't think I did for the.
Well, you can come up and look at the exams if you want.
Yeah.
Yeah.
I think I did better.